Hello students, today we're going to solve a differential equation. Use the example we began solving last time. This was the amusement park ride, compartment of mass m, and once it bottoms out and it travels to the right on that surface, it experiences a braking force to the tune of minus kV. So E part I, so here's E part I. And it says, write but do not solve the differential equation for the velocity as a function of time. So we typically begin with a statement of Newton's second law. So the sum of the forces equals ma. And in the sum, we only have the one force, and that's minus kV, because it acts to the left. And since the velocity is decreasing, because of a decreasing force, the acceleration is be rendered variable. So we have mass times a variable acceleration, so we'll express the acceleration as dv by dt. And that is as far as we needed to go for part I. Now, double I, they state here, solve the differential equation you wrote in part I. Okay. In solving this differential equation, we have to separate the variables. And separating the variables, I'm going to multiply by dt, both sides. And I'm also going to divide both sides by m. I like to park all the variables, or excuse me, the constants to the one side with the dt. It makes the algebra simple. You can complicate things if you don't do that. So there's my advice. So minus k over m dt, and then dividing both sides by v, we have 1 over v dv. So we've separated the variables by isolating the velocities on one side, and in this case dt and the constants to the other side. Now, in solving this, we're going to take the integral of both sides. So integrating both sides, setting the limits of integration. So the left-hand side, 0 to t. So we're going to start the variable force at time equals 0, and then understand the velocity at some time later t. In a similar fashion, the motion of this compartment is starting with v naught once it reaches the bottom, and then looking at to what extent its velocity is at that time later. All right, now let's integrate both sides, or at least integrate the left-hand side. So the integral of minus k over m dt from 0 to t comes out as k over m t. I'm not going to bore you with the valuing from 0 to t. It's simply t in for t minus 0 in for t. So it simply comes out to minus k over mt. Now, the other side, the integral of 1 over v dv, and I'll write it up here as a special integral. So the integral of 1 over u du is equal to the natural log of u. So we're going to follow that algorithm. So integral of 1 over v dv is the natural log of v, evaluated from v naught to v. Evaluating v naught to v, we get the natural log of v minus the natural log of v naught. Knowing your properties of logarithms, log v minus log v naught is equal to the natural log of v over v naught. Okay. Now let's consolidate a little bit here. So in the lower left-hand corner, I have minus k over mt equals the natural log of v over v naught. Now this is an okay form, but a more usable form in terms of the function of v. V as a function of t. We're going to transform this into exponential form. So watch carefully. I'm going to rewrite minus k over mt, and I'll draw this in red. I'll place it up here. We have minus k over mt is equal to log base e, because the natural log is shorthand for log base e of v over v naught. Now watch carefully. I'm going to use green, and this is my counterclockwise sort of motion here in transforming log base e to exponential form. So e raised to this left-hand side is equal to v over v naught. Okay, e raised to the minus k over mt is equal to v over v naught. Okay, so let's write that in blue. So I'm going to return to my blue pen. So we have e raised to the minus k over mt is equal to v over v naught. Now this v is technically the velocity at some time later. So here we have it. Solving for the velocity as a function of time is equal to v naught times e to the minus k over mt. And there you have it. There is the differential equation solved for a function that relates the velocity in terms of the due to a braking force minus kb. All right. Have a good night.